This is going to be a big full-on session of the trig content now. And there is tons of trig in the year 13 part of the course, as you're aware. So we're going to actually kick it off with radians, the graphs, and try and just cover all the main ideas, because this is massive. And this is kind of really where it starts feeling like the challenge in A level that it actually is. So pure maths, trigonometry, we're going to be looking at trig graphs and some of the ideas behind what's going on. Trig equations, reciprocal trig functions, so sec, cosec, and cot, double angle formula, compound angle formula, and rearranging. So there's quite a lot to cover, and a lot of it is very much year 13 content. Right, so to begin with, just the kind of key ideas. Every exam board, AQA, OCR, and EdXL are all going to expect you to have this understanding of radians, of the graphs, how to solve, and so on. So let's start with radians, a nice, hopefully really clear recap of what they are. Now, the definition, 1 radian is the angle formed by a circular arc at the center of a circle where the arc is equal to the radius. Now, basically what we're saying then is that they're equal length. So if this was a radian, that would be equal to that, would be equal to that. Okay. And so it's kind of the true definition of an angle. So if that is the radius, that is obviously the radius as well. This is our angle. Now, if S is equal to R, if I say S is like the arc length, if S was equal to R, it would be 1 radian. If S was actually equal to, half the circle, then what we'd have is we'd actually have 2 pi radians. So this is the bit that confuses a lot of people, is people think that pi and 2 pi means something different when we're dealing with radians. They don't. What they actually mean is that's the amount of that angle. So 1 radian itself, if you were to convert it from degrees, is approximately 57.3 degrees. Okay, almost 60 degrees. So a radian is about that much. It's the angle so that this would also be equal to this, would be equal to this. It's the true way of defining an angle. So that if, imagine you're in the circle, the arc is the same length as how far you are away from the arc. That would be 1 radian, about 1/6 of a circle. So 2 pi radians, 2 pi is roughly 6. 6 lots of this, or 2 pi lots of this, is perfectly a straight line. That's what that's saying. So 2 pi radians is 180 degrees. Okay, and this is where the circumference of the circle being equal to 2 pi r kind of comes from. Sorry, 2 pi radians is a full turn. Pi radians is 180 degrees. So pi, 3.14 times this would get you 180, and 2 pi times it would get you the full way round. So pi and 2 pi are like the amounts of the radians that you have. So that's really crucial to understanding the definition of a radian. Now, we are just so used to working in degrees that we never think of like these angles as pi and multiples of pi, like 45 being pi over 4, 3 pi over 4, and so on. But they are actually pi's, multiples of pi is like the perfect way to deal with it, because you're breaking a shape into radians. So the radian is the true definition of an angle. And the point of it is that 1 radian is defined so that the radius is equal to the arc length. And then we look at multiples of that. Okay, so that is normally for most people quite a new idea in year 13, but it's getting familiar with the graphs again, working in radians. So here's your trig graphs. If we look at the sine graph here, obviously the peaks and troughs is 1 and -1. But instead of using 90, 180, 270, and so on, we're going to go pi over 2, pi, 3 pi over 2, 2 pi, and so on. So we're going to write in multiples of pi over 2. So remember as well that from one position to the next, we would normally say it like repeats every 360, or we could say every 2 pi radians. That's the kind of period of the graph. Okay, and the range, which is given up here, is that, oh no, it's doing this funny thing again. Sorry, guys. Let's give this a go again. The range, as we said, is from -1 to 1. So let's have a little look. Here we go. Hopefully that's back up. Right, so here we go. This is the graph. And from this, from the key features, we can work out things like sine of theta is the same as sine of pi minus theta. That's like, as you've seen with 180, minus 180, all those kind of rules you've deduced before. Many of you would have learned like cast diagrams. That's another way of dealing with it. I just find it's easier to either use cast or the graphs rather than learning loads of little rules. So knowing where the symmetries are is really, really important. And likewise, if we move on to the graph of cos, basically we can recognize the cos graph as a translation of the sine graph. So we would normally say it's like move 90 to the left, or pi over 2 radians is the shift to the left. So that's where this kind of identity can come from as well. This literally is graph transformations. So that's what we've got going on there. And again, the range is from -1 to 1. So the graph exists between those values, oscillates between those values. Now, the tan graph is the one that's a bit different because obviously it's asymptotic. So it has asymptotes, pi over 2, 3 pi over 2, and so on. And it has actually a period of 180. It repeats like every 180, which those of you that have done cast diagrams will have seen that before as well. And another key thing is, yes, noticing the asymptotes. And this situation here is like for when n is an integer. This definition is true. And it's just important to pay attention that we know where the asymptotes are. So there's graph breaks. Now here, the range is actually anything. Like this goes from negative to positive infinity. So quite different from the sine and cos graph, sine and cosine graph. Here we go. So just some key values. You might recognize these from GCSE. There are patterns to this, but these are ones that we should sort of stand out in our mind that they're like really exact things. So even if you think, oh, I can't remember these anymore, can't commit them to memory, I just use my calculator, fine. But the thing it should be flagging up to you is try to keep these exact. Like in the exam, don't be putting loads of decimals if they're nice, perfect ones. And remember as well, just be quick at converting in your head the equivalents in degrees. So these are kind of like key ones to know. No. Again. Let's try it again. Sorry guys, I'm going to sort this very soon. 270 and 360 are the next two there. Hopefully that's back up. Right. So let's look at this exam question. What I'm actually going to do for this one is give you a couple of minutes. It's a free marker to try this yourself. Obviously use your calculator and try and get this done. Try and fill this in, see if you can get there, and then we'll work through it together. So I'm going to give you a few minutes to work ahead of me. And in the meantime, I'm going to try and sort this pen out so I can keep annotating it with you. But the following figure, so you should be given the graph for a sine x plus b, where b is between 0 and pi over 2. And it says, given that the curve has a maximum at 5 pi over 12 root 3, find me the values of a and b. For those that were in the session yesterday, it's a similar question, but it's harder. It's kind of this idea of I've got some values to sub in. It's very like graph transformations. And then it says sketch the curve of y equals a cos of x plus b on the same axes. So once you've found a and b, you can do that same graph transformation on there. So I'm going to give you a couple of minutes to think about this one. Key considerations is compare the graph you're given to sine x. Your key data is those values that we've been told there. And we also need to recall the properties of the cosine graph for that follow-up mark in the second part of the question. So as I said, a couple of minutes, give this a try, and we'll see how we go. So yeah, in about a minute, we'll go through this together. Just want to be quiet and give you some thinking time. Brilliant. Okay, so we'll start to look at this together now, I think. You're given the graph. I'm not sure if on your copies you've been given that maximum point, but you're obviously given that in the question. So you can make sure you can see that at the top there. So we know a specific value to plug in. We know 5 pi over 12 and root 3 is the maximum. So that's actually really useful that we know that's the maximum value. Let's look at how we can use that. So here we go. So y is equal to a sine x plus b, and that's the point we're using. So you can fill this in on either that slide or on the next page, and recall the properties of the sine function. So what we know is that f of x is sine x. That normally has a maximum at pi over 2, 1. So what we know is actually that that particular point is normally the maximum. So that point is getting mapped to this. Okay, that is the new maximum. So that's actually a point we can track that's moved. That's what we're going to compare. So if we compare the y values of the maximum, that'll kind of give us the stretch scale factor. So because it would normally have a maximum of 1, and now it has a maximum of root 3, y has been stretched by that factor. Y has been stretched by root 3. So if you remember from graph transformations, the y stretch is the bit outside. So that's the a value. A must just be root 3. That's just from a direct comparison of it would be at 1, but now it's at root 3. Okay, so that's part of it done. So we can now half fill in the a sine x plus b bit as this. So we now know it's root 3 sine x plus b. So now if we compare the x values of the maxima in a very similar way, this is what we've got. It would normally be at pi over 2, and now it's at 5 pi over 12. So let's think about what's happened here. Okay. And so effectively, that transformation has happened. So we can work out that b is pi over 12. And of course, if you've got graphing calculators and you've got ways of checking this, you can use that as well to kind of confidently move on and know that you've got this right. But it is very much a comparison, this kind of question. So what we know, and for the second part of the question, we were asked to then use those same letters, those same actual values to transform the cosine graph. So it's basically your answer will be the cosine graph translated pi over 2 to the left. So this is what we'll have. Sorry, pi over 2 to the left. Yeah, so what we'd have here is it's going to have moved that way. Okay, so comparing that, let's look at what the original question was. So sketch A cos x plus b on the same axis. So we now know A and we now know B. So it's the same shift, but to the cosine graph. Right. Okay. So we're going to look at some other trig functions here. We're going to look at arcsine, sec, so the inverse trig and also the reciprocal trig functions. And obviously there's a few more identities to look at as well with this part of the course. So we're going to go through from scratch and then we'll also, again, do another exam question. So the inverse trig equations, this is really important to start with, that we use the correct names for these. So if y equals to sine x, then the inverse we actually call that arcsine of y. Okay, so that's how you'd write it in your calculator. That's what the function's actually called. So even better if you can call it that in the exams, arcsine, arccos, and arctan. Okay, so the other key thing to remember is that this is not this. Okay, the notation is very similar. This is an inverse function. When we're talking about sec, which is 1 over cos, you would actually have to think of that as cos x to the -1. That would be 1 over cos. And that one is actually called sec as a function. So that's a really important thing that we don't mix the two up, because that on your calculator, that could cause us some problems. Right, okay. So when you're asked to give an answer in a certain range, there might be multiple values because it's periodic. So we're going to look at solving now. Now let's take an example. So to find the other values, we look at the symmetries and the period. So here we go. For this one here, if we've got sine of x is a, so I'm saying that the y value here is a, then actually there could be multiple x values that works for. So they could be talking about this, could be talking about this. They could even be talking about this, or any infinitely other answers. Okay, so they will need to give you in the range that they want. So even in that range, there's 4 potentials that could be. So what we're going to do is first one, to find the principal value, that's what we call it, x1 is equal to arcsine of a. Okay, now that is the first value your calculator will give you, and we call that the principal value. So normally it will give you this one. Okay, so that is called the principal value. Now x2, the second value, will be pi, or 180, minus your x1. That'll give us that one. Now, if we think about the ones I've called x3 and x4, that would be, because this repeats every 2 pi, And this is basically 2 pi away from this. This one will be just x1 minus 2 pi. I'll tell you what, let's color code it even better. And x4 will be the x2 one minus 2 pi. Okay, now some of you might have worked from cast diagrams. You might actually like using the graph like this to do that, but that is exactly what we're doing. So it's a shift in that way. And you've used the symmetries and you've used the period of the graph in order to do that. So very well done. But they're your 4 potential answers. Now, I know we've done this very generally. It's much nicer when you actually have some numbers because then you can sort of check them and stuff. But this is just showing you sort of how it behaves from the symmetry and the periodicity. So let's have a little look. So what I'm going to do, we're going to move this into more trig equations like this, but hopefully we can appreciate that because the graphs are all slightly different, we either use the cast diagram or we sketch the graph and we look at how they're behaving to pick up the other solutions. So let's move this on. So sometimes we'll need to solve equations of that form in a range, and this is the one that hopefully you'll remember. We sort of have to adjust the bounds. We have to adjust the bounds for theta because of what's going on. So again, I'll color code this for you. So if sine, let's say theta equals C, then the first value, theta 1, second value, theta 2. Well, the principal value is going to come out as inverse sine of C. And then theta 2 will just be 180 minus theta 1. And that's all fine. The thing we have got to remember about these bounds is that this is going to be a lots of the original bound plus b. And this is going to be a lots of the original upper bound plus b. So basically what we've done is we've had to transform these in this way. We've had to actually change the bound. So if it was 2x plus 50, you'd have to double the lower bound and add 50, double the upper bound and add 50, and shift where you're looking so that when you minus 50 and half it at the end, it's back in the correct domain. So yeah, so that's what you've got to do. And then when you found your 2 answers or whatever, do that transformation in reverse to both of them. So when you want your final x1 and x2 at the end, you're going to take your answer theta 1 minus b from it and divide by a. And likewise here, take your theta 2 minus b from it and divide by a. Okay. And there could be other values, but in that range, we just find them all and then do the transformation back right at the end. Okay. So this is very like heavily theoretical with no numbers. What I'm actually keen to do now is please make sure your calculator is in radians, as it probably wants to be for the pure content as a default. And I'm going to give you a few minutes to try this question here. So it's a free marker. It does say very specifically, find the exact solutions to the following equation for theta in the range minus pi over 2 to pi over 2. And this is going to be, yeah, the transformation is 3x plus pi over 4. So we want to solve cos of 3x plus pi over 4 equals a half. Key considerations, it says exact. So please make sure you look out for that. And also more than one solution is what we've got to look out for. Okay, cool, because we've got an interval to look at. Give you a minute and a half, and then I'll start working through it with you. But very well done. Thank you again to everyone for working along. It's quite full on content already, first thing in the morning. So really, really well done. Cool. Okay, so we might approach this in different ways because obviously some people with graphical calculators, it's really helpful to see the graph and you might sketch it yourself. Some people use cast diagrams. Let's start looking at how we preserve the exactness and what we're actually expected to write on the page. So it is quite a few bits to this. Immediately, if you're going to solve this using your calculator and you want to find the first value your calculator would spit out without the graph, you would just do arc cos of a half. And remember, that would give you 3x plus pi over 4. Now, arc cos of a half, we should recall that is an exact one. That is pi over 3. Now, what you've got to be really careful with here is as it gets more convoluted and you add a different multiple of pi and then you divide it by 3 and you do that, the calculator might start doing it in decimals because it doesn't actually know how you want to leave it. So that's why we need to be really careful. Now, the graph side of the calculator is great for checking because if it gives it as a decimal, you can just check it's the same. But we do need to preserve this exactness. So we get pi over 3, and that's sort of your first mark. Now, we also need to extend where we're searching. So we're not just searching between minus pi over 2 and pi over 2. We actually need to times those bounds by 3 and add pi over 4. So are we all happy that this is actually where we're searching between? Okay, which looks like a horrible number, looks horrible bounds. But even if you want to put those in decimals and just see roughly like what that is, we'll just keep looking round to it so that if the number gets beyond that, we don't include it. So it might be worth tidying that up, and that tidies up to minus 5 pi over 4, 7 pi over 4. Okay, so please do make that a note of that step because this shows the examiner you know where you're looking. You're not just aimlessly picking some, you know where the boundaries are. Okay, so that's where we're going to extend our search. And as I said, write them as decimals if it helps to the side to go, okay, that's sort of numerically where I'm going up to. Now, what we'll do is, yeah, this is where we need to think about the properties of the cosine graph. So some of you, as I said, might have used cast. Some people might have sketched a graph. But the way the cosine graph is, if we've got pi over 3, it's the same amount back from 2 pi. So from the end. Okay. So if you think about the period of it, that's how it's going to repeat. So the next one is going to be there. And if you went from the other way, you also know minus pi over 3 cos is symmetric around the y-axis. So there's your other one as well, near your principal value. So there are a few of the first solutions you get. Now remember, these are solutions to 3x plus pi over 4. These aren't the final answers, but they're all in the interval that we have and that we want. Okay, so let's make sure we got a note of those. Because now with those solutions, which are in that interval, which are between minus 5 pi over 4 and 7 pi over 4, you want to now shift them back, so minus and divide. So taking those three solutions, pi over 3, 5 pi over 3, and minus pi over 3, we want to minus pi over 4 to get what the potential answers are for 3x. And then, of course, divide them by 3. And that should put them back in the original domain. Now, if you use the CG50 or use a calculator where you could actually go and look at these values and they gave you it as decimals, obviously use that as a checking mechanism, but we want to have preserved the exactness. So if you gave them as decimals, you would probably lose this final answer mark because the question explicitly said exact. So that is screaming out, try and keep it in terms of pi. Okay, I think that method was really important there because it also conveys exactly what the examiner would expect to see. Brilliant. Okay. Really, really well done. Hopefully we're working through this point in the book together. We're about to go on to the page on reciprocal trig functions. So I don't know if they're numbered, but this might be like the 32 one on the trigonometry slides. But reciprocal trig functions is what we're moving into next. So I will also just make a note that there is a mini mock at the end of each section for you to practice follow-up questions. And after you kind of do the survey on how you found the session, we'll send all the solutions out to you so you can fill that in or check your answers. Right, brilliant. Let's keep pushing on. So reciprocal trig functions. This is very new for a lot of people. Whoops. At A level. And it's very easy to confuse. Like I've taught classes this and they've gone, no, I think you're wrong. And because I've said cosec is 1 over sine, it's the third letter, remember, of each function that tells you which one it links to. So cot is tan, sec is 1 over cos, cosec is 1 over sine. Okay, and it's really important. Now, I would actually argue that these should be identities. These should be identically equal. They're effectively definitions. And likewise here, these are identities as well. And these two identities are actually off the back of one is equal to sine squared plus cos squared, because if you divide through, it tidies up to that. So if I show you what I mean, if we had 1 equals cos squared theta plus sine squared theta, feel free to fill this in, and we divided all of that by cos squared theta, it's handy to remember this derivative, this derivation rather, that would become sec squared, that would become 1, and that would become tan squared. So if you ever forget it, because you know this sine squared plus cos squared is 1, you can divide through by cos squared, and you can generate this here. And as you can guess, or hopefully you've seen it before, if you do the exact same thing, but you use sine squared, you get the other one. So if we divide everything through by sine squared theta, you get the other one. And I think it is good to know some derivations, just in case in the exam you panic and you forget, and then you go, oh, I don't know if I've got that right or not, if I've remembered it correctly. So does that make sense? Hopefully that's all clear. Okay, so these reciprocal trig functions, we've got to be confident dealing with. And in my experience, most people like them better than they like arccos, arcsine, and arctan. Even though they don't explicitly exist on your calculator, you can do 1 over the function. But understanding their graphs is really crucial because they behave in a really kind of quirky way. So let's look at their graphs. So here are the graphs here for cosec, for sec, and for cot. Now, some people are so used to drawing these off the back of the sine, cos, and tan graph, they think they have to draw the sine, cos, and tan graph as well. You don't, but why we often do it is to help you. I mean, you shouldn't, but it helps you work them out to start with. So basically, they exist around the sine, cos, and tan graph. So if you've got the sine graph that exists between -1 and 1, 1 over 1 is 1, and 1 over -1 is -1. And then because they're reciprocal graphs, it's 1 over. As sine, cos, and tan will get smaller, they're shooting off to infinity. So these are actually really cool graphs whereby they exist asymptotically above and below the sine wave, because and what's really weird about them is their minimums are bigger than their maximums. So their local minimum is floating above the local maximum. So they're really weird, cool, different kind of graphs. And they have asymptotes as well at these points. Now, the other thing to define is their range can be written as y is greater than the modulus of 1. Sorry, let's get that right. Modulus of y is greater than 1. So basically, bigger than or equal to 1 or less than or equal to -1. Okay, they don't actually exist between 1 and -1. So this is a very strange range when you think about it. It's like the middle part of the graph has been rubbed out. It's been wiped out. They don't exist for numbers like a half and a third and 4/5. They only exist for 1 and above and -1 and below. And that's actually very much the same for sec, because sec is a translation of cosec in the same way that sine is a translation of cos. So exact same thing. And again, the range is that the y is greater than or equal to 1. Okay. Now the tan one, so cotangent, cot, is a really strange one because it's obviously asymptotic, but also the asymptotes and the zeros swap round. So basically where cot has an asymptote, tan has a 0, and vice versa. Oh, here we go again. Stop that. Right. I think I've discovered, guys, it's a certain part of the screen that I shouldn't be writing on. So we can fill the tan graph in. Now, what I'm saying is you don't need to draw the tan, sine, and cos graph on. They're normally used to help you get started drawing. But if you can actually just learn how these graphs look, that's what we want. That's what we need to do. So cotangent actually behaves very like tan in a way, just a sort of transformation of it, because it already has asymptotes and zeros. And do check you can access these like on your calculator as well. But they're not actually there as buttons and functions themselves. That's what I'm getting at. Okay, so we're going to look at solving some trig equations where they've got reciprocal functions. So sometimes the trig identities are needed to solve equations. For example, this one here. Notice it's in radians, and we'll need to kind of identify the identity that we need. Now it's got tan squared and it's got sec in it, and we know that there's an identity that involves tan squared and sec. So we know that 1 plus tan squared is sec squared. And I would say probably a rearrangement of this would be useful. So if you think about it, sec squared theta minus 1 is tan squared. And it's probably the tan squared we want to replace, because we can't replace sec. It's so often a lot of people think, oh, I'm going to replace the sec part, but it's actually the tan squared that's easier to replace. Create a quadratic problem in terms of sec. Let's do this together. So we'll fill this in as 2 sec squared theta minus 1 plus 3 sec theta equals 0. And then we're going to get 2 sec squared theta minus 2 plus 3 sec theta is 0. Have I messed that up? No, it is plus, isn't it? Yeah. And now it's one of these sneaky quadratic ones in disguise. which we could factorize. And if you'd rather use a substitution and call x sec theta, and then it's like 2x squared plus 3x minus 2, it would actually factorize as 2x minus 1, x plus 2. And if we re-put that back in, that would be 2 sec theta minus 1. But I'm sure from this point, it's a quadratic. You can solve it how you want using that substitution. So even if you called it x, that's fine. Now, this is the bit we need to interpret carefully. So this is the part where we need to say, okay, so either sec theta equals 1/2 or minus 2. Now, interestingly, we know from the range of those functions, sec theta can't equal one of those things. It can't actually equal 1/2. But you don't necessarily need to jump from there. Let's just convert this to what we really want, which is cos theta. So that would mean cos theta would have to equal 2 or minus 1/2. This is the problem, isn't it? In the same way that sec theta can't equal 1/2, that's because cos theta can't equal 2. So this is the solution set we're looking to explore. Cos theta equals minus 1/2. Okay, so we're going to keep going. But hopefully that's clear up to there. Please, like, as I said, do ask any questions, do message in if there's anything that's unclear. But it'd be great if you're annotating this along. Because again, you can imagine this is a classic A-level question. Just looking at it, it's trig, quadratic, identities, and it's solving, and it's in radians. So there we go. So to go on from there, you'd solve for theta in that range. Right, let's actually get onto this so you can do one yourself here. So a nice little free marker. I'll give you again, 1.5 minutes, and then I'll catch up with you. By forming a quadratic in cosec, so they were kind of prompting you as well, and maybe you want to look back at your identities, solve the following equation. So give your answers in terms of sine x. So actually, you don't have to fully find x. You just have to give your answers in terms of sine x. So remember, that's key thing. We need to recall identities. And it's just said give solutions in sine x. So that's nice as well. So as we said, I'm going to give you 1.5 minutes. Give this a try, and then I'll catch up with you and see how we go. Right, guys, let's check this together. Really good one for us to have tried. And I can't stress this enough. This kind of trig practice, identities, equations, is really important, even if you think you're still at the point you're taking too long with it. It's almost about struggling for it before the exam, so it doesn't cost you time in the exam. It's better taking too long now. That's what the practice time is for. So let's have a little look. Here's the question. So we've got 3 cosec x is equal to cot squared x minus 17. And then what we're going to do is think about the identity we need, which is cosec squared is 1 plus cot squared. And sometimes we need to rearrange that, but it's the cot squared we can replace. So cot squared is cosec squared minus 1. And just do be really careful you put it the right way around. So cosec is like, so 3 cosec x is equal to cosec squared minus 1 minus 17 as well. So let's look out for that. And then basically get the quadratic tidied up all in one side. And check we agree. We got cosec squared x minus 3 cosec x minus 18 is 0. And check your minus signs are right and all that as well. There's your first mark. So if this was out of 3 marks, almost seems quite harsh that this is only 3 marks, but once you rearrange it and you've got a quadratic, like we said before, quadratics aren't going to give you a lot of marks because you've got your calculator. It's all the kind of other stuff around it that we need to do correctly. So factorize and solve. So this does factorize. Even if it didn't, you can still do it on your calculator. You can use a substitution if that helps you. So if you want to think of cosec as y or u, and you do u squared minus 3u minus 18, factorize that, put cosec back in, that's fine. Now, from these factors, we can deduce that cosec is either equal to 6 or minus 3. And remember, you should already be thinking, can it be both of them? And actually, for this one, yes, it can. They are both in the range of cosec. So we do, of course, need to put it back for sine. And this is actually the end of the question. It didn't ask for x. It said find it in terms of sine. So 1 over sine x is cosec. And cosec is 1 over cosec is sine. So if you do the reciprocal of each of those answers, sine x is a sixth or minus a third. And that is it. That's all the question wanted you to do. And there's your 3 marks. So very, very well done if you got to that stage. Please do fill this in if you were just finishing that part off, because obviously we're going at a fairly snappy pace. We've got the next little bit of trig to look at now, which will take us up to the point we're going to break, I think. Oh no, sorry, we've got quite a bit of trig to go. We're going to keep going with this trig session up to lunch. So where we're going to go next is we're going to look at the compound angle formulae. So double angle, addition formula, and all of that stuff. And see how we get on with this. So hopefully that's down. Your answers are good. That was all clear. And we can move this on. So now we're going to look at addition formula, double angle formula, and that sort of thing. And this stuff does just keep coming back with a vengeance, particularly for integration and differentiation as well. So again, all the exam boards since the 2017 reform, but even before, have always included this stuff in there. So it's a real exam favourite. It's a real key A-level topic. Now, looking at the compound angle formulae, most of you will be given this in a formula book, but like I said, do check it's in there. They might use A and B, they might use alpha and beta. But basically, the addition formula for sine is that the sum of the angles is sine A times cos B plus the other way round. And there's kind of 6 rules hidden in 3 because they give you the plus minus version, and just look out for when it's the other way round. Okay. Now also remember, do want you guys to recall, and I'm trying to write on the bit of the screen that it doesn't mind, is that tan alpha plus or minus beta, you can also think of this. We don't want to forget that this is allowed as well, using the identity, and that can be part of the derivation as well. Don't forget that that is a thing. I think for some people, they get so caught up in the addition formulae that they forget, obviously, the normal trig identities apply as well, and tan is still sine over cos. Okay, so tan alpha plus or minus beta is equal to sine alpha plus or minus beta over cos alpha plus or minus beta. So that is true as well. And then from these stem the double angle formulae. Now, what I just want to point out to everyone, because they're not explicitly given in the formula book, but you can derive them really quickly, is don't forget that if you want to derive the double angle, you can just put in the letter as the same thing. So sine of 2 alpha is like sine of alpha plus alpha. So you can use the double angle and you just end up with 2 sine alpha cos alpha. And then the cos double angle actually will give you cos squared alpha minus sine squared alpha. What I do want to just point out with this one is that there are actually 2 versions that stem from this. So there's like 3 forms of the double angle for cos. This is really important, and some of you that have gone on and done integration and stuff will have met the reasons we need this later on. The double angle formula for cos is the most user-friendly, most useful format because it ties in with the identity. So cos of 2 alpha, because we know 1 is identically equal to sine squared plus cos squared, what this allows us to do is we can replace this bit or this bit and therefore get the double angle for cos exclusively in terms of cos or exclusively in terms of sine, making it quite versatile and quite useful for different identities. So these are 3 versions of what we call the double angle for cosine, because they allow us to manipulate and change either sine squared using this identity or cos squared using this identity, because of course we know that sine squared is 1 minus cos squared. So if I replace that in there, I'd end up with cos squared minus 1 minus cos squared. The minus minus cos squared makes 2 cos squared, and I get this version of it. And likewise, if I did cos squared alpha is 1 minus sine squared alpha, and I replace that in there, I get 1 minus 2 sine squared alpha. So you might be thinking, why do we need all these 3 different ways? Those of you that have done the practice of integration later on will see that this is really useful for lots of different things. But effectively what we're getting at is, if I take this example, 2 cos squared alpha can actually be rearranged with this double angle. And we'll kind of do this quickly and then park this for later on. If you plus 1 across and then half it, cos squared alpha is equal to a half cos 2 alpha plus 1. The reason I'm just pointing this out now, you might be thinking like, is he just doing that for the fun of it? This is really useful for integration. It's a lot easier to integrate this than it is to integrate this. So for things like integrating and differentiating cos squared and sine squared, you can use this version of the double angle to help you integrate later on. And that's why I'm pointing that out. So this doesn't just exclusively come up in trig questions where it's just like identities and proof and solving trig equations. This is actually an underlying technique that's going to save us a lot of work later on with the calculus. And then also, obviously, the tan double angle, same thing. You just put alpha and alpha into the addition formula for tan, and you get this. So really well done. Hopefully that's like clear. Please make those annotations because this is really where the addition formula is important and useful. So there are a few kind of key points, but it's really the double angle of cos that's the most useful and involved one. What we'll do now, though, is we're going to do a quick question together where it's actually a prove that. So it's one of these kind of show questions, work from the right-hand side to the left or vice versa. And this one is a really important one to set out and check we're good with. So here's the question. It might be over your page. You might have already given it a go. Please feel free to. Prove that the following identity, So cos theta plus sine theta over cos theta minus sine theta is identically equal to sec 2 theta plus tan 2 theta. And when we see 3 marks, we might be thinking, I couldn't do that in 3 minutes right now. Like in an exam, I'd be really struggling for time. Don't stress about that. Sometimes we do need to spend a bit longer, but it's better to go through that now and understand and anticipate how long it really will take you, and also where to start. That can be sometimes the problem. So we need to work from one side to the other. It's a proof. So we do need to just clearly show everything we're doing. Don't jump any steps. Even if you've convinced yourself what's going on, convince the examiner. And it's going to involve double angle. Okay. So again, minute and a half, maybe 2 minutes, and then I'll give you that head start and then we'll just push through it together. Let's see if we can get somewhere with this. Right, guys, I'm just going to give you another 30 seconds or so, and then we'll check this. We're going at a brilliant pace, so there's no rush. And I do actually want to give everyone the opportunity to fully see this question through. So think about the double angle. That might inform you with what side to start on. And then we're going to whiz through this together, but really well done. That's great. Right, guys, as I said, we're kind of well ahead of time. So we're going to go through a few more questions, and then there's the mini mock. Then we'll take like a break for lunch, which will be quite early, but obviously, as I said, everything's shifted forward today. And then this afternoon, we've got differentiation, integration, and then we'll be looking at like hypothesis testing and some of the really hard stats content. So let's check this question through for now. Let's see how we go. And then after this, we'll talk about some of the harder questions you can practice. If you have any questions, let us know as well. So here we go. Right, so going through, we've got, let's start with the more complicated side of the identity. What I would actually suggest is where there's more that can be done. Like look at the side where you can actually do some stuff. So the left actually doesn't look very useful. The right, at least we have double angle and we have things we can replace. So I would start probably with the right-hand side for this question, sec 2 theta plus tan 2 theta. Another little hint, it's not always true, but I would say if you've got one side that's a single fraction and another side with 2 bits, try and aim to get to the fraction. That's another little technique or hint that you could use, because it can be tidied up. You can do common denominators, you can use identities. So that could be something that you want to do as well. So the first step would be sec 2 theta plus tan 2 theta. We get 1 over cos 2 theta plus sine 2 theta over cos 2 theta. And then actually, what's really nice about this is you already do have that common denominator. So we can combine that fully as 1 plus sine 2 theta over cos 2 theta. So let's check we're happy up to there. Are we all good with that? So 1 plus sine 2 theta over cos 2 theta. So that's our first bit. Hopefully we're all good with that. Now from there, this is the next step we're going to move on to. We've still got to sort this out a bit, and we've got some double angles we can just plug in now. So let's check we're happy with this. So I'm going to just move this on to the next step. So since we know the double angle for sine and cos, we can replace those in that question. So we have 1 plus 2 sine theta cos theta on the top, and cos squared theta minus sine squared theta on the bottom. Okay, so that's literally from the single fraction you just formed. That is a case of combining it and making it now with the double angle. So we've just got theta instead of 2 theta. Right. Now from here, this is what we're aiming for. This is what we've currently got. So we want to try and manipulate the right-hand side here to look like this. Now, this is quite tricky at first, but we've got to think about factorizing techniques. Now, something I would maybe make a note of right now as a little hint for these questions is lots of the identities we've seen can be factorized as a difference of 2 squares. So if you think about like this in itself, that's the hint straight away. Cos squared minus sine squared can be a difference of 2 squares as a double bracket. But don't forget, guys, that like sine squared, which is 1 minus cos squared, which is 1 minus sine squared, tan squared, which is sec squared minus 1, all of them can actually be put in a difference of 2 squared brackets, which can often be really useful for cancelling things out in a double bracket for fractions. So if we start thinking about how this factorizes and looking at the link over there, that might really help us factorize the bottom. So what we've got is the top can be rewritten in the following way. Now I'm going to come back to the top because you might think that's not obvious at all. But if we focus on the bottom and recognize that the bottom can be factorized as cos theta minus sine theta times cos theta plus sine theta, and kind of use the answer we're working towards to see what's disappeared, we can see that a cos theta plus sine theta has cancelled, which may well be a factor of the top. Now the top has a few identities in it, because 1 can be thought of as sine squared plus cos squared. And you might then recognize that this is potentially a double bracket. It's handy to know. Oh no, there we go again. Some key bits of the screen it doesn't like me writing on. Sorry about that. Here we go. Hopefully we can see that again. So what we were saying is, if you've got a situation where you've got like x squared plus 2xy plus y squared, that will go in a double bracket, x plus y, x plus y. And that's kind of like what we've got here. Something squared plus something else squared plus 2 lots of the combined. That's a repeated double bracket. That's actually what we call a perfect square. So on the bottom, we've got dots. We've got a difference of 2 squares, which we've spotted, hopefully. But on the top, we've got something squared plus 2 lots of the combined plus the other thing squared. That's a repeated double bracket. So what we're getting at is this. This is how it would factorize. Now, there's actually no problem in looking at what you're aiming for and using that as sort of to help you factorize it as well, especially if you've already picked up what the bottom bit factorizes as and what kind of must have cancelled. That can basically tell you what needs to be on the top. So although it feels like a bit of a cheaty way of doing it, they will then cancel and it works. Okay, so tidied up, you then arrive at the left-hand side. So the proof is complete. And there's your final mark. So that was really a really good way. What I'll do is I'll maybe go through an alternative way that we could have done this, starting with the left-hand side. Some of you might have done that and thought, oh no, am I wrong starting on that side? Let's have a little look. Now, starting on the left-hand side, you would actually need to introduce those other factors. So I think this is a really hard one to preempt and go, oh, I'll just design to times it by the same thing over itself. And that'll probably help me. Because obviously any equivalent fraction, you're timesing by 1 in a clever way. You could have done these steps in reverse. I think it's much harder to have seen that and done that this way around. So this way, yeah, so this is basically like the reverse steps. But what I do think is really important to stress as exam technique is you should, of course, look for the easiest side to start on. So if there's more going on the right, if you think, right, there's double angle, there's 2 things that can become 1 fraction, try and do that. And that only comes with practice. But the biggest bit of advice I think I've given you there is the thing about the difference of 2 squares. A lot of the identities can be factorized in that way. And for these fraction questions, that cancels loads of stuff out. So hopefully that's all clear. Right, let's keep going, because this is another big topic off the back of what we just done. Right, so hopefully we've all got this in our booklets as well, and we're ready to sort of go through and annotate. This is the kind of r cos theta plus alpha form, or r sine theta plus alpha form. And this will be massive for modeling. Now, remember, modeling, there's a huge emphasis on trig modeling now. So this skill we almost need to anticipate is going to be a big one for us to do. So if we think about what's happening here, let's have a little think what we need to include. Now, we need to think about the principal value. So alpha will generally be in radians and in a sort of principal value domain. And R will be like a greater than 0 value. That's normally what we're looking at. So these can help us solve or sketch something that previously we would have no idea. If it said 2 sine x plus 3 cos x, sketch it. That's really hard to do and imagine. But if we get it all written in terms of sine, it's much easier to visualize that as a single wave function. So that's what we're going to look to do. Now, what we're going to first use is the double angle formula. Oh, sorry, not the double angle formula, the addition formula from your formula book. And I would actually always go through the process of doing this. I've got loads of students that I teach that try and shortcut this, and it ends up messing up a minus sign, and then the whole question goes wrong. So all we're doing is we're taking the addition formula of sine and timesing it by r and going, this is what I want. This is what it would actually be equivalent to if I expanded it out. And now I'm literally going to compare coefficients. So what I know here is that r cos alpha, all of that stuff must basically link to the original question, a sine x. So more specifically, let's do this even better. That and that must be equal to a because it goes with sine x. So you're just comparing the bits. And then likewise, these bits here, do you know what? That would have been prettier if I color coded it, wouldn't it? Let's do that. So r sine alpha goes with b. And what color will we use in purple? So that and that goes with a. Okay, and then I'll fill this in bog standard. So cos, nope, sine alpha, sine x, and cos x. Okay, now so what we're saying from this is basically that a equals r cos alpha. Can you see that? Yeah. And b equals r sine alpha. Okay, now that's kind of crucial. Now this, and as I said, some of you might think, I'm really confident with this. This is absolutely fine. I've done loads of these. That's great. Sometimes with a minus sign and stuff, it's just worth taking this time to just show the examiner as well, because it's so easy for any of us to mess this up when we start throwing numbers in. And they like to make these questions particularly hard with the context. So what we're going to do is we're now going to form the equations we need. So like we said, A is r cos alpha, B is r sine alpha, and r and alpha, these are actually just constants. So determine alpha, we know that the two expressions can kind of be divided by each other because we can work out tan. So basically what we're saying is if I take B and I divide it by A, then basically what I'm doing is I'm doing r sine alpha over r cos alpha. So alpha is equal to basically arctan of B over A. And that should hopefully give a principal value for alpha somewhere in the stated domain. Okay. Hopefully that's good. And then likewise, so that's quite a nice thing to do, but again, show this like explicitly as well. So then the next thing we've got is to find R. And this is the bit that people just kind of do in a rote fashion really quickly to get themselves the mark. But R is basically the two things squared and added up because the sine squared plus cos squared is 1, factorizes out. So effectively what we have is that if we know that a squared plus b squared is r squared cos squared alpha, getting too excited here, I need to slow myself down, plus r squared sine squared alpha, I can factorize out an r squared. So basically, that's just 1. So a squared plus b squared, oops, equals r squared. So then we know okay. because we knew that that was 1. So it's good. Right. Now what we'll do is we'll look at this in the context of a graph, and then I'll give you a question to try and work through. Then that'll take us up to the mini mark. I'll have a little sort of checkpoint with you before we take a break for lunch. And then this afternoon, as I said, we're doing differentiation, integration, and some hard statistics as well. So yeah, here we go. So thinking about the graph here, if we now have transformed this a sine x cos b cos x thing, this will help us sketch the graph. Because remember, of course, the maximum point, which is quite a key feature, that maximum will be linked to the value of r. And that's what's very easy to forget. And the roots are some other points that we're going to want to find. Again, if you've got calculators that can do this, this is great. But look at the question will be designed with that in mind. So these are like the roots. They might be important features. And also the minimum. And sometimes if this is some sort of model, they might want the y-intercept. If, for example, the x-axis was time and they ask what's happening at time 0, they're basically asking you for the y-intercept. So we've got to like pull this back in terms of the original graph. But getting it in that form really helps us to do that. So the y-intercept might be an important thing as well. What we'll do is we'll actually just do quite a bog standard, get it in the form question. And I'll give you maybe 3 minutes to do this. It's a 5 marker, so it'd be like 5 minutes in the exam we'd want to dedicate to this part. Here's the question. Solve the following equation for x in the range minus pi to pi, cos x plus root 3 sine x equals to 5 marks. Let's think about what we need to look for. It can be transformed into that format. That's probably how I'd recommend it. Actually, you could have used r cos theta minus alpha or plus alpha. I'd recommend this for this one. There might be multiple solutions for x. That's why they've given us a specific set of values to look for x. But yeah, what I'll do is I'll give you 3 minutes now to give this a little try. So just going to check the time. Yeah, give it a go. Thank you so much already for paying such close attention to what we've done. Give this question a try. I'm going to give you a head start. And in 3 minutes' time, we'll start working this through together. Here we go. Well done again, everyone. Thank you so much for working alongside us in this. As I said, a couple of minutes still. So I'll give you 2 minutes. We'll check in. We'll see how we're going, go through the answers, and then I'll give us a bit of an update with a plan for calculus this afternoon and hypothesis testing. Really well done. Right, let's keep going. Right, okay, so guys, what we'll do is we'll start to go through some of these questions. We're going to look at this one now. One thing I would like to point out, so just to really reiterate the whole point of this skill, let me just annotate this. I'm going to use a red pen here. Just the thing that should be flagging why we need to do this. Why is this important? Being able to get something with cos and something with sine just written in terms of sine or just written in terms of cos is really, really good, because then we can solve it like a year 12 trig equation, or we can sketch it as a graph. If there's a cos floating about and a sine floating about and maybe a number or an equation, it's very difficult to deal with if we can't rearrange it into one thing. So what I would say is we're focusing on the left. This question isn't particularly scaffolded, but if we focus on the left to begin with, and we say, let's get that just in terms of sine, then worry about it being equal to 2. That will then allow us to solve it. Okay, so let's work this through together. So first thing, let's get it in the terms in the form r sine x plus alpha. So in the very same way that we just looked at this, I would think about the addition formula for sine x plus alpha, and I would equate that. Now look at the coefficients of cos. Coefficient of cos is 1. The coefficient of sine x is √3. So r sine alpha, which are the bits that go with cos x, if we look at these, r sine alpha, they must be equal to 1. And r cos alpha must be equal to √3. Okay. Once we've got that set up, we can then, of course, go on and find r and find alpha. So, and remember, this question was in radians, so do make sure you're in that correct radians mode. Let's have a little look then. So, now I do just want to say, going back to the previous question, you could have used r cos x minus alpha or plus, but it would have come out negative. But what we're saying is they didn't tell you in this question. The value of r would end up being the same. The value of alpha would be different. But ultimately, it will still give the same answer. So for those of you that are wondering or asking, how did he know to use sine when it didn't say, you could have used either. I've just chosen sine because I think it would be nicer. Right, let's have a little look then. So let's check how we got on. Hopefully the part for r was easy. It's basically like the Pythagoras. So you square it, sine squared and cos squared is 1. So that factors out. √3 all squared is 3. 1 squared is 1. So then we square root it. We get r squared is 4. So r is 2. So it's a stretch of the sine graph or cos graph by 2. So we know it oscillates between 2 and -2. So that's good because r is greater than 0 as we wanted. So r is 2. Right, now the next bit, determining alpha. Remember, you can use r sine alpha over r cos alpha, which tidies up to tan alpha, and that would be 1 over √3. That is actually a very exact trig ratio. That turns out being 30 degrees, or in radians, pi over 6. So we've now found alpha. Now, if I put this all together, and I combine this, the actual format we have is we now know that this thing can be written as this. Can I just point out, we have totally ignored this 2 up till now, because we've just been dealing with the left-hand side, and we've managed to write it just in terms of sine. That was what we were trying to do. So it's now at this point, we can go, right, this is all of this stuff. Let's put this back into the question. So actually 2 sine x plus pi over 6 is equal to 2. So we can divide both sides by 2. That's the trig equation we're solving. And it's very like a kind of year 12 one, except of course, it's not degrees, it is in radians, but it is something we should be able to solve. And we're asked, remember, to solve it for the correct domain of x. So let's do that last little step. Well done if you've done it. And honestly, really well done to everyone for persevering through all of this trig already. First thing, before we get into the calculus and the heavy afternoon of pure maths, and then the hypothesis testing. So solving this, arc sine of both sides, find your principal value, rearrange, and pi over 3 is the one that works for the correct domain. Now, what I want to show you as well, hopefully you've got access to this in your booklets, is at the end of each topic, there's like a mini mock with some questions. So what I'm going to do is I'm going to give you a chance now to have a little look at these mini mock questions. I'm going to catch up with you in maybe sort of 5-10 minutes and then explain what's going on for the rest of the day. But try these out. Do message any questions in because I'm here as well. But look at the mini mock paper and then I'll go through the running order of the day as well. Because as I mentioned earlier, everything's shifted an hour forward for today. So we're going to start lunch a bit earlier and then we'll be back for differentiation. So I'll re-put up the timings. Let's give a go to this mini mock though. Here are some questions. And yeah, let's see how we go. So I'll catch up with you guys in about 5 minutes. Okay, so we do another sort of 3 minutes or so, give these a try. And then I'll go through a couple of these. There are actually more questions in your pack. And so we'll check a couple of these together before taking a short break. Just give you a bit more thinking time. What I do just want to encourage is that particularly for question one, where it's like a lot of tedious tidying stuff up, you've just got to persevere with these. From my experience, marking students' work with this stuff, they sort of give up because they think they're doing it wrong. Please don't with this one. It is just using the addition formulae and the stuff we've learned. So I'm going to be quiet, let you carry on for a couple more minutes, and then we'll check through. And it should be a really good solid checkpoint for this trigonometry. Really, really well done, though. Keep going. Okay, yeah, so that first part is quite tedious. We will check this very soon. See how we go. Okay. So you're using the addition formula, but actually what we'll find is we probably need to use some double angle as well. And then part two, similar, it's quite tedious, quite tricky to check. But I would really like to look through part one with you in a minute. So if we're there with that, great, crack on. I think there is a third question as well for you guys to try. As I mentioned, all of these solutions will be sent out to you. So at the end, when you get a link for the survey to say how you found today, once you fill that in, you'll get all the solutions to everything in this booklet for these mini mocks, because we have one at the end of each session. So it should consolidate everything we've covered in that session. Right, so another minute or so, and then we'll start checking question one. That'd be great. Cool. Right, okay. So let's check this first one. So, oh, there we go, all in one. There's the answer. So here's a suggested method, but basically split it up so that we have sine 2x plus x, and then apply the double angle. Now, the one thing I would try and encourage is don't do too much in one step. Firstly, in case you go wrong, and secondly, in case the examiner is like, well, the mark scheme is quite prescriptive. Because this was only a couple of marks, you could have probably condensed this into a couple less steps. But it's another thing about exam technique for this as well, is I would drop a line down and probably use like an identically equal symbol and just go down a line each time. You basically don't want to work along the page because it's too messy and it could actually lose you some marks. So ultimately, we get it as 3 sine x minus 4 sine cubed x, because the question asked us just to get it in terms of sine x. And sine cubed x is still in terms of sine x, because it's like sine x all cubed. Okay, so that is absolutely fine. So very well done if you got that. But do just make sure there was quite a few rounds of having to use both the double angle of sine and the double angle of cos there as well.